This video is for Chemistry in the Earth System, Unit 5.2, Solutions. Today's essential question is, how are concentrations of solutions using molarity, mass percent, volume percent, and parts per million calculated? So let's begin with a concept that is essential in both laboratory work and real life. Solution concentration. Now, whenever you make a drink like lemonade or iced tea, you are essentially preparing a solution. The sweetness or tartness depends on how much sugar or lemon juice you dissolve into a specific amount of water. In chemistry, we need to describe this amount precisely using numerical values. That's what we mean by concentration. It's a way to quantify how much solute, again, the solute is the stuff that you are dissolving, so how much of that solute is present in a given amount of solvent. Usually, the solvent is something that's a liquid like water. Not always, but most of the time. We'll focus today on several ways chemists describe concentration, including molarity, molality, mole fraction, mass percent, volume percent, and parts per million, which is abbreviated ppm. Each method has its own strengths and ideal case uses. By the end of this lecture, you'll understand how to calculate these things and know when to use each. The most commonly used method for calculating concentration in chemistry is molarity. This tells us the number of moles of solute. Remember, 1 mole is a specific number of particles, just like a dozen is 12. It tells us how many moles of solute is dissolved into exactly 1 liter of solution. The formula is simple. Capital M, representing molarity, is equal to the number of moles of the solute divided by the number of liters of the solution, standardized to 1. So, if you dissolve 1 mole of sodium chloride, which is NaCl, into 1 liter of water, you'll have a 1 molar solution, represented by 1 and then capital M. But why is this useful? It's useful because reactions in chemistry often depend on how many molecules are available to interact. Knowing the molarity lets you precisely control the number of reacting particles. But there is a catch. Molarity depends on volume as well, and volume can change with temperature. For example, if your solution gets warmer, it might expand slightly, decreasing the concentration. That's why molarity is ideal for room temperature lab work, but less so in experiments involving heating or cooling. Next, let's talk about mole fraction, which is especially useful in thermodynamics and gas mixtures. Unlike molarity, mole fraction is not affected by temperature because it doesn't use volume or mass, only the number of particles. So the formula for mole fraction is X, capital X representing mole fraction, is equal to the number of moles of solute divided by the total moles of solution. Notice that they're both mole values. This will always give you a value between 0 and 1. You can think of it kind of like a percentage of how many of the molecules in the mixture are the solute. For example, if you have a mole fraction of 0.2, it means that 20% of the molecules in solution are the solute. Mole fractions are crucial when dealing with vapor pressures, boiling points, and gas mixtures. They are also used in Dalton's law of partial pressures and Raoult's law, which describes how mixtures behave. Now, let's explore molality, which is another method that's especially useful when temperature changes are involved. Now, unlike molarity, molality does not rely on volume. Instead, it measures the moles of solute per kilogram of the solvent. So the equation would be, in this case, a lowercase m is equal to moles of solute divided by kg of the solvent. Because mass doesn't change with temperature, molality is ideal for studying things like boiling point elevation and freezing point depression, which are properties that depend on the amount of dissolved particles. For example, when roads are salted in the winter, it lowers the freezing point of water. Chemists use molality to calculate exactly how much salt is needed. It's also used in pharmaceutical and industrial formulations where precise control is essential regardless of environmental conditions. So let's look at an example using sodium chloride or table salt. Suppose we dissolve 0.250 moles of sodium chloride, NaCl, into 3.61 liters of water. To find the molarity, we divide moles by liters. So capital M is going to be equal to 0.250 moles divided by 3.61 liters, which is going to give us a value of 0.0693 moles per liter. This means that we have a 0.0693 molar solution, which is pretty darn dilute. Now, if we're going to calculate the molality, we need the mass of that water. Now, we know as a general rule that generalizes pretty well, 1 liter of water weighs about 1 kilogram. So we'll use a quick rough substitution here. So because of that, we know that 3.61 liters of water is equal to 3.61 kilograms of water. So we can calculate the molality by plugging in 0.250 moles, but then dividing by 3.61 kilograms, which is going to give us a value of 0.0693 moles per kilogram. Now, do you see how both the values match here? That is because we assumed that the solute didn't change the volume, and we are using water, which has a very easy definition. Again, it's not always true. It changes with temperature somewhat, but in general, at room temperature, 1 liter of water weighs about 3.61 kilograms. Next, we calculate mole fraction. We need to know the moles of water if we're going to calculate mole fraction. So we will need to convert the 3.61 kilograms, or 3,610 grams, into moles using water's molar mass, which is about 18 grams per mole. So in order to accomplish this, we'll take the 3,610, right, 3,610 grams, and then divide by 18. When we put that into the calculator, we get a value of about 200.377, depending on how many significant figures we want to keep. But we're not done. That is not the mole fraction. We then add the solute, right, which is, in this case, the 0.250 moles of sodium chloride, remember from the problem? We'll add that to the number of moles of water, the solvent present. And so we're going to add the 200.377 moles of water to the 0.250 moles of sodium chloride to get 200.627 moles total for the total solution. So when we go to calculate the mole fraction of sodium chloride in this solution, we're going to take the 0.25 moles and then divide that by the 200.627 moles, which will give us a value of 0.001246. Now that is a very small mole fraction, which is, again, if you turn that into a percentage, would be about 0.125%. Now, let's say you have a very concentrated solution that you want to make weaker. This is called dilution. For example, if you have 5 liters of a 2 molar hydrochloric acid solution and you want to dilute it into 20 liters, what is the new molarity? We will use the formula M1 times V1 is equal to M2 times V2. Once we have that, we can plug in the numbers. So if we're solving in this case for M2, right, the molarity of the new solution or the second solution after we've done the dilution, we can solve the equation algebraically for M2. So in this case, M2 would be equal to the 2 multiplied by 5, and then we would divide by 20. And that would give us a new molarity of 0.5 molar. So by quadrupling the volume, right, we went from 5 liters to 20 liters. By quadrupling the volume, we quartered the concentration, meaning the concentration was about 1/4 as strong. So let's shift now to mass percent, which is another useful way to express concentration, especially in food science and industry. Mass percent is the mass of the solute divided by the total mass of the solution, then multiplied by 100 to get it to be a percentage. So mass percentage is equal to mass of the solute divided by mass of the solution times 100. For example, if you dissolve 5 grams of salt into 95 grams of water, the total mass is now 100 grams. So the mass percent would be 5 divided by 100 grams, then multiplied by 100 to turn it into a percentage, and that would give us 5%. This method is very straightforward because it only requires a scale, no volumetric flasks or pipettes, which is nice. It's also temperature independent, which makes it more reliable for many real-world applications. Next up is volume percent, which is used mostly for liquid mixtures. For example, rubbing alcohol is often labeled 70% isopropyl alcohol. This means that there are 70 mils or 70 milliliters of alcohol in every 100 milliliters of the solution. So volume percent is going to be equal to the volume of the solute divided by the volume of the solution, then multiplied by 100 to turn it into a percentage. But be careful here. Liquids don't always add linearly. If you add 50 mils of ethanol to 50 mils of water, you might not get exactly 100 mils because of the way that the molecules pack together when they're mixed. So the volume percent tells you what portion of the final volume is made up by the solute that you're studying. Now, when solutions are extremely dilute, like pollutants in water, for example, we tend to use parts per million, or ppm. And this is basically a mass ratio scaled up to the millions, right? ppm is going to be the mass of the solute divided by the mass of the solution, which by itself is going to be a pretty small number, but then we're going to multiply that by 10 to the 6th power. Now, we're using the 10 to the 6th power because that is in fact 1 million. Right, remember, this is parts per million. And so we're taking the mass of the solute, dividing it by the mass of the solution, right? So we're going to get parts, but we're going to standardize it to 1 million, so then we're going to multiply by 10 to the 6th power. So let's go through an example before we finish up. Say we dissolve 5 grams of baking soda, which is sodium bicarbonate, into 2 liters of water. Since water weighs about 1 gram per milliliter, that is 2,000 grams because we have 2 liters, or 2,000 milliliters. The total solution mass is going to be 5 grams plus the 2,000 grams to give us 2,005 grams. Okay? Now, the mass percent, we're going to take the 5 and then divide that by the 2,005, right? The mass of the entire solution. Then we're going to multiply that by 100 to turn it into a percentage. And so we have 0.2494%. That's the mass percent. The ppm, or parts per million, we're going to take the 5. We're still going to divide it by the 2,005 grams, right? The total mass of the solution. But we're going to multiply it by 10 to the 6th power, right? To standardize for parts per million. That's going to give us 2,494 parts per million. Now, These kinds of solutions are used for things like antacids and environmental pH buffers because of the small numbers. So to wrap up, here's what you need to remember. There are many ways to describe concentration, and each has its own purpose. Use molarity for everyday lab work, like in a high school chemistry class. Use molality when temperature might be changing. Use parts per million for teeny tiny amounts of solute. But always check your units. Make sure that you're standardized using grams and not mixing grams and kilograms. Make sure you're using all liters and not milliliters on accident versus moles and molar, right? Make sure your units are standardized, so show your work. And most importantly, understand what the numbers mean in real world terms. A number without context won't help you in the lab or on a quiz. At this point, you should be able to generate a full and appropriate response to today's essential question. How are concentrations of solutions using molarity, mass percent, volume percent, and parts per million calculated?